Okay, good morning. This is our 18th lecture. In the previous few lectures, we have discussed particularly about the oblique shock waves. Okay, so today what we will do, we will try to see some of the numerical problems which will cover what happens to properties on the behind the shock waves, and also we will try to see the perspectives of shock reflections. Okay, and some of the physical inferences if we can make from these numerical problems, that we will try to do at the end. Okay, so let's do our first problem. So first problem statement is, we have a given geometry. So geometry is something like this, that I have a plane of surface, and then it is having some compression corner which is at an angle of 16 degree. Okay, and after this what I have, actually I have nothing but another wall which is parallel to this initial surface. Okay, and it is given that we have this theta as 16 degree, and initial Mach number m1 is given as 2.8, p1 is given 1 atmospheric pressure, and temperature at point 1 is given as 519 Kelvin. So these are the given parameters. Okay, and what we have to do, we have to determine four parameters. First we have to calculate m3, t3 and p3. So these are the three parameters, and along with this figure one important angle is prescribed over here. So it is given that from this compression corner we will be having formation of a shock wave. Okay, so this is our shock wave. So say this particular shock wave is making some angle beta 1 with this surface. Okay, so now what will happen, my flow streamline will be something like this. Okay, from point 1, this is a flow streamline. Now this streamline will deflect at an angle of theta, which is given over here as 16 degree. Okay, and after this as I will be having some reflected shock wave also. So say this is my nothing but the reflected shock wave. Okay, and when streamline will touch this reflected shock wave, so once again it will deflect at some angle. So say it will become parallel to nothing but this new wall. Okay, so now if you see, this particular streamline was supposed to go in this direction if shock wave was not present. Okay, so it means this direction and shock wave, whatever angle these will make, that will be nothing but my angle beta 2, that will be angle beta 2, and this particular direction and this new direction of streamline, whatever angle these will make, now this angle will once again be nothing but theta. Is this one clear? So this direction of the streamline and shock wave will make beta 2 angle, and streamline between its earlier direction, extended direction and new direction will make an angle theta. Okay, in this geometry one more parameter is given, that the angle which shock wave is making with this top wall, that is nothing but phi, and you are also supposed to calculate the value of phi. Okay, so this is our problem statement. Is this problem statement clear to all? Okay, so now if we see, first thing what we have to do is, we have to actually, if we have to find out the properties. Okay, so what I can do, this is my point number 1, then in between, after the flow has reflected, gone behind this incident shock wave, then say I have properties designated by 2, and then these 2 will actually once again interact with the reflected shock wave, and in the downstream I will be having properties designated by 0.3. Okay, so if I have to calculate this value of P2 by P1, T2 by T1, etc., and M2, what I need to first calculate, I need to determine the shock angle beta. Okay, so shock wave angle beta I have to determine. Okay, so for calculating beta, what I have to do, I have to use theta beta m relation. Fine. So if we see over here, in the upstream of this oblique shock wave, Mach number is known to us. So m1 is known, and then theta is also given as 16 degree. So theta is also known to us. So if we substitute these two in our theta beta m relation, then because beta I cannot explicitly find out, so I have to do some iterative procedure. Okay. Another possibility is that if in place of going into this relation, if I directly go to theta beta diagram, okay, so on this theta beta diagram I will be having some line like this. Say this is corresponding to Mach number 1, okay, and I have now value of theta as 16 degree. So corresponding to this 16 degree I will be getting two values of beta from here, okay. And as I told you earlier, that unless or until there is a very high back pressure, we will not be having presence of strong shock waves, okay. So there are high chances that always weak shock waves will be favored, okay. So corresponding to weak shock wave, I will get this particular value as nothing but my value of beta 1. Is this point clear? So what I have to do now, from this point, for theta equal to 16 degree and Mach number equal to 2.8, we have to refer theta beta m diagram, okay, and from this diagram if we do calculate, I will be finding value of beta 1 as nothing but equal to 35 degrees. Is this point clear? Now we know that the relations whatever we have derived for normal shock wave, these will be applicable. The only difference is that we have to consider Mach number in direction normal to this wave, okay. So here this is my Mach number m1. If I have to consider mn1, considering these geometrical parameter, I have already given the details that mn1 will be equal to m1 into sine beta 1, okay. So if you do calculate this value, it will comes out to be 1.606. Is this point clear? So this is the value what we are getting over here. Now this value we can utilize to find out the value of normal Mach number in the downstream of this wave mn2, okay, because we have seen relation that mn2 square is equal to mn1 square plus 2 divided by gamma minus 1 divided by 2 gamma by gamma minus 1 mn1 square minus of 1, okay. So from here if you calculate, you will find, so value of gamma is known to us for air as fluid. So value of gamma is known to us, that is 1.4, and values of mn1 just now we have calculated. So if we do substitute over here, we can actually calculate this mathematical number, okay. So the value over here comes out to be 0.6684. So this is my mn2, okay. Now once I have the value of mn2, it means I have now Mach number in direction normal to this, okay. So this is my mn2. If I have to calculate m2, so m2 is in this direction, fine. m2 is along the streamline. So relation between mn2 and m2, can you tell me? I have already explained you in the previous discussion. What will be the relationship? m2 will be nothing but equal to mn2 divided by sine of, you simply see this thing, okay. So this is your m2, fine, m2, and this is your shock wave. So between the shock wave and m2, angle has become beta 1 minus theta, fine. This angle is theta, this complete angle with horizontal is beta. So in between this streamline and this particular shock wave, angle is beta minus theta. So if m2 is in this direction, normal component will be m2 into sine of beta minus theta. So simply I can write that m2 equal to mn2 upon sine of beta 1 minus theta. So So this is a simple geometry. Even by referring to this figure, I can actually predict this value. Okay. So M2 from here will comes out to be 2.053. Okay. Is this point clear? I have the value of M2 now. So now, what is the situation? Now I have this second shock wave, reflected shock wave. For this shock wave, my upstream Mach number has become M2. Is this point clear? So for this second shock wave, now upstream Mach number is M2. So, and what is the flow deflection angle? Theta. So theta is the same because this theta and this theta are same. These two lines are parallel. So theta over here is same. So it means that for reflected shock wave, we will have that theta equal to 16 degree and upstream Mach number M2 is equal to 2.053. So corresponding to these two values, if I refer to theta beta M diagram, I will get the value of beta 2. So from here beta 2, if I calculate, that will be nothing but 45.5 degrees. So if you do remember, I have explained to you that if we are having a weaker shock wave, and then if I change the flow Mach number, if I decrease the flow Mach number for the same value of theta, then our value of beta increases. For strong it decreases, but for weak it actually increases. So you can see with this numerical number, earlier the value was 35 degrees and now this beta 2 is coming out to be 45.5 degrees. So it is actually increasing over here. Up to this point, is it clear? Now what we have to do? Whatever we have done for the incident wave, same thing we have to do for the reflected wave. Okay. So for reflected wave, if you see, I have to now calculate value of Mach number which should be normal to reflected wave. So can you tell me what will be the value of Mach number normal to reflected wave? So with this reflected wave, this Mach number M2 is making an angle of beta 2. Okay. So its normal component will be nothing but M2 into sine beta 2. Fine. So please, now you have to differentiate in between this Mn2 and whatever Mn2 I am writing over here now. Whatever the previous Mn2 I have considered, this is normal to the incident shock wave. Now we are talking about the reflected shock wave. So when I will be considering now Mn2, that will be nothing but normal to the reflected shock wave. Is this point clear? So I am writing over here, say Mn2, and let me use as a superscript R to designate that this we are considering for a reflected shock wave. So Mn2R will become nothing but equal to M2 times sine of beta 2. Is this point clear? So if we do calculate this value, it comes out to be 1.46. Okay. So if I have this value, then can I calculate Mn3? Can I calculate Mn3? Mn3 will become nothing but Mn3 square equal to Mn2 reflected square plus 2 by gamma minus 1, 2 gamma by gamma minus 1, Mn2 reflected square minus 1. So from here, if you calculate Mn3, it will comes out to be 0.7157. Is this one clear? Is this one clear? So if I have value of Mn3, can I calculate M3? What will be M3 now? Tell me. Mn, no, M3. Mn3, see, Mn3 I have calculated. Mn3 upon sine beta 2 minus theta, correct. Is this point clear, or do I explain geometrically? So if you see, this is my M3, and M3 is making angle with this shock wave as beta 2 minus theta. So its normal component will be M3 times sine beta 2 minus theta. Is this point clear, or do I explain with different diagram? Okay. So M3 will become then Mn3 by sine beta 2 minus theta. So beta 2 we have calculated, Mn3 just now I have calculated. From here I will get value of M3 as nothing but equal to 1.45. So my one part is solved. I was supposed to calculate the value of M3. Okay. Secondly, it is asked to determine the value of P3 and T3. Okay. So for calculating P3 and T3, first I must calculate P2 and then I will be able to calculate actually this thing. Okay. So can you tell me, for an oblique shock wave, if I have to calculate P2 by P1 for first incident shock wave, what will be the relation? Please tell me. P2 by P1 will be 1 plus 2 gamma, yes, Mn1 square minus 1. Okay, so this is the value of P2 by P1, and if you calculate this, it will comes out to be, so Mn1 is known to us. If you do calculate, it will comes out to be 2.82. Okay, it is 2.82. Similarly, the relation for T2 by T1 is, T2 by T1 is nothing but P2 by P1 into rho 1 by rho 2. So rho 1 by rho 2 will become over here gamma minus 1 into Mn1 square plus 2 divided by gamma plus 1 into Mn1 square. Okay, so if you do calculate from here, T2 by T1 will become 1.38. Is this point clear? This value will comes out to be 1.38. Similarly, I can calculate P3 by P2 for the reflected shock wave. So when I am calculating P3 by P2, we have to take care of one thing, that when I will be considering this Mn over here, I have to consider Mn2 corresponding to reflected wave. Okay, so if you calculate this, this will comes out to be 2.32. Similarly, you can calculate T3 by T2. So I will not write detailed formulation. It will comes out to be 1.294. Fine. So we have calculated these two ratios of pressure for both ratios of pressure and temperature for both incident as well as the reflected shock waves. Okay. So now with this information, what I can say that P3 can be P3 by P2 into P2 by P1 into P1. So P1 will cancel, P2 will cancel. I have these two numbers and P1 is given as equal to 1 atmospheric. So from here I can see that my static pressure at point 3 will be 6.54 atmospheric. This is my second answer. Okay. Similarly, I can calculate T3 as T3 by T2 into T2 by T1 multiplied by T1, which will be equal to which will comes out to be 932 Kelvin over here. Okay, and then one last part is left, which is I have to calculate the value of phi. So if you see phi over here, it is nothing but, see, this angle is beta, this angle is theta. So if you see this shock wave with horizontal, how much angle it is making? Beta 2 minus theta. What I am saying, this angle, complete angle is beta 2, with horizontal this angle is theta. Okay, so this is a horizontal line With this horizontal streamline, the shock wave is making angle beta 2 minus theta, and this angle phi is also designating angle made by shock wave with this boundary. And as this streamline and this boundary are parallel to each other, so this angle will be the same. So I can say from this geometry that phi will be nothing but equal to beta 2 minus theta. So from here I will get the value of phi as 29.5 degrees. So this is my problem is done. Okay. Is this one clear? Now let's talk about the second problem. In case of problem number 2, what we have compression corner at an angle of theta 1 equal to, sorry, angle is written as theta 1 over here. So let me write it theta 1 only. Okay, and then I have another surface over here, and with this surface is also having compression corner at this point, but this compression corner, this particular compression corner is at actually angle of some another angle theta 2. Okay, and it is given in the question that we have a formation of shock wave which is starting at this point and ending at another compression corner. So shock wave is something like this. Okay, so obviously this shock wave will make an angle of beta 1 over here. Fine. And then it is given that when this shock wave is reflecting, it is reflecting something like this. So this is the reflected shock wave. Okay. Fine. Now if I take a flow streamline, that is something like this with Mach number 1. So here all the properties are designated with point 1. Then this will deflect at an angle of theta 1. It will go something like this. All properties in this region are designated with point 2, and then from this second shock wave, once it will deflect, and now it will deflect at an angle of, it will deflect parallel to this another solid boundary. So it will go like this, and this is say my station number 3. Okay, so now if you see, this particular streamline is extending in this direction. This is the extension of the streamline. With this extension, whatever angle shock wave is making, that angle will be nothing but beta 2. Okay. So this extension is making certain angle over here, and this particular angle is nothing but my beta 2. Is this point clear? Are you clear with this? And what about this angle? What about this angle? This particular angle in between the direction of the streamline and with this deflection. So particularly if you see, this deflection with horizontal boundary is making an angle of theta 2. Is this point clear? This deflection with horizontal boundary has made an angle of theta 2, because this is the angle. This is at angle theta 2. So if I consider at this point a horizontal parallel line, so my streamline which is deflected, this will make angle theta 2 with this horizontal boundary. So angles theta 1 and theta 2 as well as beta 1 and beta 2 are clear to you? Okay. Now let's see. So this diagram is given in the question, and along with this diagram few more parameters are given. So first parameter is given is, it is given that Mach number at point 1 is 3, pressure at point 1 is 1 atmospheric, temperature at point 1 is 300 Kelvin, value of theta 1 is equal to 14 degrees and value of theta 2 is equal to 10 degrees. So theta 1 is equal to 14 degree, theta 2 is equal to 10 degrees, and you are supposed to find out the values of M3, P3 and T3. So now problem should be clear to you. Okay. So what will be the next step? Because we have already done a problem, so you should be able to answer now. What will be the next step? We have theta 1 equal to 14 degree, M1 is equal to 3. We will refer to theta beta M diagram, and from there we will find the value of beta 1 and we will choose a weak angle, okay, corresponding to weak shock wave. So you will find value of beta 1 as 31.2 degrees. If we have calculated this, then my Mn1 will be equal to M1 times sine of beta 1, which is coming out to be 1.56. Then I can calculate Mn2. What will be the formulation? Mn2 square is equal to Mn1 square plus 2 by gamma minus 1, 2 gamma by gamma minus 1, Mn square minus 1. So using this formulation I can calculate the value of Mn2, and Mn2 will be 0.6809. Okay, is this point clear? Once we have Mn2, can I calculate the value of M2? What will be M2? Mn2 upon sine beta 1 minus theta 1. So over here we have different angles. So first one is designated as theta 1. So this will comes out to be 2.30. Okay. So for first wave all of you are fine. For first wave what we have to do, we have calculated, and even if I want to calculate the value of P2 by P1 and T2 by T1, that also I can actually calculate. For the first wave, okay, I can also calculate from here the values for P2 by P1 and T2 by T1. Can you calculate these values? So we can easily calculate the values for these two parameters also. Okay. Now we have to go for the second wave. Can you tell me how to find out the value of second wave angle beta 2? Once again we have to refer to theta and M diagram, theta beta M diagram. So M value we have calculated. M2 is how much? Just now we have calculated 2.30. We have to now calculate theta. So what will be theta for the second wave? Can you tell me what will be theta for the second wave? Please tell me. Will it be equal to theta 2? See, when we are talking about the deflection, we are considering deflection angle as angle between the streamlines. So say this is the direction of upstream streamline and this is deflected streamline. So this angle is theta 1. Now for reflected wave, if you consider, this has become upstream streamline and this has become downstream streamline. So this is the extended direction of the upstream streamline and this is downstream streamline. So the deflection of streamline is actually this complete angle. Fine. Deflection of streamline is nothing but this complete angle. Okay. So if you see with horizontal, this streamline has deflected at an angle theta 2, and with horizontal this first streamline was moving at an angle theta 1. So this total angle between the two streamlines will become nothing but theta 1 plus theta 2. Is this point clear? So it means that for the case of this reflected shock wave, if you consider the total deflection angle between the streamlines, that is nothing but theta 1 plus theta 2. Point is clear? Are you able to understand this point, or do I repeat it? You have to consider the angle between the two streamlines. Okay, so angle with horizontal surface is theta 2, but between the two streamlines it is becoming actually theta 1 plus theta 2. So deflection angle is always supposed to be in between the two streamlines. Okay, so in this situation I will get that value of theta for total deflection for the second case is nothing but equal to theta 1 plus theta 2, which is equal to 24 degrees. Okay, so angle is 24 degrees, this is 2.30. So if I refer to theta beta m diagram, what I will get from here? I will get the value of beta 2, and this beta 2 if you do calculate, it is coming out to be 52.5 degrees. Okay, so once again you can see your beta 1 was 31.2 and beta 2 is 52.5. So angle has actually increased. Okay, so is this point clear? So beta 2 is 52.5. Now can you tell me what I have to calculate? Now I have to calculate Mn2, which is normal to the reflected shock wave. So that will be nothing but equal to m2 times sine of beta 2. Okay, so from here if you calculate this value, it is comes out to be 1.82. If you have this value, then can you calculate Mn3? Mn3 will be nothing but Mn2 reflected square plus 2 by gamma minus 1 divided by okay, this will be your Mn3, and if you calculate Mn3, it will comes out to be 0.6121. Fine. If Mn3 is known to me, can I calculate M3? M3 is Mn3 divided by sine of beta minus theta. So beta 2 minus theta was nothing but theta 1 plus theta 2. Okay, so that was the total deflection. So from here if you calculate M3, it will comes out to be 1.28. Okay, now can you calculate P3 by P2? This will comes out to be 3.698. I will not explain you, you can do calculate by your own. Okay, because it is simple now. So P3 by P2 and then T3 by T2, it will comes out to be 1.547. and now if you have to calculate P3, that I have already explained to you, it will be P3 by P2 into P2 by P1 into P1, and if you calculate, finally its value comes out to be 9.88 atmospheric. Okay, and similarly if you calculate T3, it comes out to be 631.6 Kelvin. Okay, is this point clear? So all of you are able to calculate this? Okay, so we have reached these two numbers, 9.88 atmospheric and 631.6 atmospheric. Anyone is having any doubt till this point? Okay, now let's try to see the next problem. So I have this problem P3. It is having two parts, A and B. So first let's talk about part 1. So in the part 1 we are considering whatever the problem number 1 we have done, exactly the same problem. So we have first flow deflection angle as nothing but 16 degrees over here, and then I have another surface over here which is parallel to this initial surface, and here this is exactly the first problem. So I am having a shock wave, okay, and this shock wave has reflected, okay. So if you just now we have solved this problem, so if you recall, this angle was beta 1 equal to 35 degrees, and if you do calculate this angle phi was nothing but 29.5 degrees. Just now we have done in problem number 1, and if you do remember, Mach number at this point was 2.8 and pressure was 1 atm, and this was my station number 2, this was my station number 3, and point 3 our Mach number was 1.45. okay, so this is nothing but my same problem whatever I have done in the starting. Okay, now in this problem it is asked that you have to calculate P03. What is P03? P03 is nothing but my stagnation pressure or total pressure at point 3. So I have to calculate P03. So obviously if I have to calculate P03, I can write it like this: P03 equal to P03 by P02 into P01 into, like this I can write it. Okay, so let's try to see whether we are able to write it or not. So if you do remember, earlier also I told you once that for calculating static properties P2 by P1, T2 by T1, or rho 2 by rho 1, I can employ the same relations as that of normal shock wave for oblique shock wave also. The only difference will be we have to consider nothing but the normal component of the Mach number to that particular shock wave. But if we calculate stagnation or static properties, because these are not specific to a particular component, when we do calculate stagnation property, ultimately the complete Mach number comes to rest, not only a single component. Okay, so the other component also comes to rest. So that's why we cannot utilize directly the relations whatever we are using for normal shock wave. Okay, so that is the reason first what I will do, in order to find this P02 by P01 only, we have to do some more exercise. Okay, so how I can find out P02 by P01? I can do P02 by P01 as nothing but, first I can calculate actually P02 by P2, because this relation is generic, available to us, that is not specific to normal shock wave. Then I can calculate P01 by P1 with reciprocal one. Okay, so this relation is also generic, and then I can actually multiply this with nothing but P2 by P1 for n. So this I will be calculating for oblique case. So oblique case means by considering the normal shock wave relation by including actually normal component. Okay, so if you see relation of P0 by P is nothing but 1 plus gamma minus 1 by 2 m square whole power gamma by gamma minus 1. So this is the relation. Okay, so in this relation, by using this relation, if I calculate P0 1 by P1, that will be 1 plus gamma minus 1 by 2 m1 square times gamma by gamma minus 1. Okay, so I have to consider the total Mach number. So from here if I do calculate, it comes out to be 27.14. okay. Similarly, I have already calculated Mach number in the problem number 1. So M2 was 2.053. Fine. So now my P naught 2 by P2, if I calculate, that will comes out to be 8.50. So nothing but here I have to substitute Mach number M2, and if and already P2 by P1 I have calculated for this first incident wave. So P2 by P1 in that problem was nothing but 2.82. So this we have already calculated. So from here I can now calculate the value of P naught 2 by P naught 1, because P naught 2 by P2 I have calculated, this I have calculated, this I am having. Okay. So from here if I do calculate the value of P naught 2 by P naught 1, that comes out to be nothing but 0.8832. Is this point clear? Similarly, what we have to do? We have to calculate P naught 3 by P naught 2. So P naught 3 by P naught 2 will be P naught 3 by P3, P2 by P naught 2 multiplied with P3 by P2. Fine. So if you see over here, already we have calculated P3 by P2 as nothing but 2.32 in the problem number 1, and then P naught 3 by P3 comes out to be 3.42. This we have already calculated. So what I will get from here, that P naught 3 by P naught 2 comes out to be 0.9334. Is this point clear? Okay, are you able to get these parameters? So now I can calculate the value of P naught 3 as nothing but P naught 3 by P naught 2 multiplied with P naught 2 by P naught 1 multiplied with P naught 1 by P1 and multiplied with P1. So here if you see 2 is cancelling, 1 is cancelling, P1 is cancelling, nothing but I am getting P naught 3. So this ratio I am having, P1 is given as 1 atmospheric. So if I do substitute, I will find over here 22.37 atm. Is this point clear? So now let's try to calculate part B. So part A is done. Now I have part B. So P3B. P3B actually is interesting. So here we will try to make some physical inference. Here it is given that I have only a single deflection, okay, and there is formation of a oblique wave, and this wave is such that in the upstream I have same Mach number of 2.8, same initial pressure of 1 atm, okay, and then I have here this as my M2, and this M2 is such that it is becoming identical to 1.45 whatever the downstream Mach number we were having in the previous part after passing through 2 shock waves. Is this point clear? So what we are considering, in the upstream and downstream of this shock wave, whatever flow conditions we are choosing, these flow conditions we are choosing identical to part A of this problem. And we are saying that this angle of deflection theta is controlled in such a way so that whatever shock wave is producing, that shock wave is actually changing our Mach number from 2.8 to 1.45. Is this point clear? So problem is identical to that of part A only. So flow properties are changing between the same limits, but in that case we were having one incident shock wave, one reflected shock wave. Here we are trying to do this with the help of only a single shock wave. Okay, and in this condition actually Mach numbers are known. This is known. This angle theta is actually unknown. So now if you see, and ultimately it is given in the question that we have to calculate P naught 3. Sorry, P naught. Now it will be P naught 2. Stagnation pressure, because if this is station 1, this is 2, so it will be P naught 2. So it is asked that we have to calculate actually P naught 2. Okay, but if I start with the question, so the question is that theta is also unknown, and this angle will be beta. Beta is also unknown. Both theta and beta are unknown, and our relation is theta beta m relation. So in a single relation I have actually two unknowns. But one interesting point is that I am having the value of downstream Mach number m2 known. Okay, so what I have to do over here, I have to actually go for a iterative procedure. How I will do iteration? First I will assume a value of theta, and corresponding to this theta I have now Mach number m1. I will calculate the value of beta, and then for this beta I will try to find out the value of downstream Mach number m2, and then that I will check if it is, how far it is from actually 1.45. Are you understanding this point? And depending upon this distance, this difference, whatever the difference we will be having from 1.45, depending upon that we will try to modify our guess. Have you understood this point? So what I will do, let me make a table. This is corresponding to theta, then say corresponding to this theta I will get a beta. This is in degrees, this is in degrees, and then corresponding to this beta I will get some value of mn1. Using that mn1, so mn1 will become nothing but m1 sine beta. Then corresponding to this mn1 I can calculate the value of mn2. Fine. And then this mn2 I can utilize to calculate the value of m2, which will be mn2 divided by sine of beta minus theta, and here I will use the normal shock relation, okay, to calculate mn2. So first I have guessed the value of 20 degrees. This is my initial guess. Corresponding to 20 degree I have got the value as 39.4 degrees. mn1 was 1.777, mn2 was 0.621, and m2 was 1.87. So it means my corresponding to deflection of 20 degrees I am getting nothing but the higher value of m2. Okay, so what I have done, I have considered now deflection angle of say 30 degrees. Corresponding to 30 degrees, if you calculate, you will get the shock wave angle of 54.7. What you have to do, our tendency is this Mach number m2 is 1.87, so it is higher. If it is higher, we have to consider slightly more stronger shock wave. So if we have to consider slightly more stronger shock wave, we have to increase the value of beta. For increasing the value of beta, I have increased over here theta. So corresponding to 30 degrees, 54.7 degrees is my beta, and 2.27 is Mn1, 0.541 is Mn2, and corresponding to this you are finding that 1.29. So it means in between we have to consider now next value in between this. So it is more closer to 30. So say my next guess is 28. Corresponding to 28 I am getting 50.8, 2.17, 0.554, 1.43. Okay, 1.43 means with 28 I have slightly gone more down. So I have to now choose slightly stronger. So slightly stronger I have gone to 27. So with 27, slightly weaker. So 27, with 27 I have got 49, 2.11, 0.56, 13 and 1.50. So it means my angle is in between these two numbers. So I know the final Mach number, that is 1.45. I can do interpolation. So I can write theta minus 28 will be equal to 1.50 minus 1.43 by 27 minus 28 times 1.45 minus 1.43. So I have come closer and then I have used the linear interpolation. So using this, if you calculate, value of theta will comes out to be 27.7 degrees. Okay, and corresponding to 27.7 degrees, Mn1 I have not exactly calculated, just I have taken the near guess. So near guess is about 2.15. Okay, so it is close to 28. So near guess is say 2.15. This is Mn1. If this is my Mn1, then I can now easily calculate the value of P2 by P1, because P2 by P1 is nothing but, for an oblique shock wave, requires value of Mn1. So by this, if you calculate P2 by P1, it comes out to be 5.23. It comes out to be 5.23, and our aim is to calculate stagnation pressure P02. So for that, first I need to calculate P02 by P2. Okay, P02 by P2 is coming out to be 3.42. Do you know how to calculate this? This is very simple now. Similarly, P01 by P1, this if I calculate, it is 27.14. With these values, now if I have to calculate the stagnation pressure P02, I can write P02 by P2 times P1 by P01 into P2 by P1 into P1. Fine. Sorry. Yeah, is this correct? No. Simply I can write this as P2 by P1. P2 will cancel and multiplied with P1. Okay. So this will give me value of 17.89 atmospheric. Now based on these values, can you make some inference, physical inference? If I start from the first point, part A, in case of part A, if you see, your value of P01 by P1 is 27.14. Okay, so for part A, you can say that your P01 is 27.14 atm. So for my part A, P01 is equal to 27.14 atm. And what was P03? 22.37 atm. Now if you consider part B. For part B, P01 is same, 27.14 atm. What about part this one, downstream pressure? 17 point. In this case also my upstream Mach number was 2.8 for both cases, and here downstream Mach number for both cases is 1.45. Fine. So, sorry, 2.8 and 1.45. So what is happening actually, if you see in first case, when you are changing your Mach number from 2.8 to 1.45, your stagnation pressure is changing from 27.14 to 22.37. In second case, when you are changing from this to this, your stagnation pressure is actually decreasing more. So it means that second situation is actually requiring or resulting in more loss of stagnation pressure to bring the same change in Mach number in comparison to case number 1. Is this point clear? So it means that in any situation, if our interest is to decrease the Mach number, it is, and if our interest is we want to decrease the Mach number without much loss in the pressure, then our better option is, efficient option is to use the combination of incident and reflected shock waves. Is this point clear? If you don't use the this one, if you use a single shock wave to achieve this, then you will be having more loss of pressure. So the many outcomes of this are, if you have a scramjet engine, okay, so in case of a scramjet engine, what we want to increase the propulsion efficiency, and we have seen in very initial lectures that the thrust force which is responsible for propulsion, that is directly proportional to exit pressure. If our exit pressure which is leaving the engine is high, then our propulsion efficiency will be better. Okay, so if say your fluid is entering at certain pressure in the inlet, if its pressure is decreasing, okay, in the initial section, if its pressure is decreasing due to decrease in Mach number, then what will happen, its stagnation pressure is decreasing a lot, then we will be finding that its exit pressure will not be that high. Okay, so because of which it cannot have very high propulsion efficiency. So in order to have high propulsion efficiency, if we have to decrease the Mach number, if we have to slow down the flow in certain situation, it is always preferred to use the combination of incident and number of incident and reflected shock waves, because this process of decreasing the flow speed will be nothing but giving us better propulsion efficiency. Why? Because it will decrease the loss of pressure during the process. Fine. We can clearly see in initial case pressure change is only about 5 atmospheric, whereas in second case it is about 10 atmospheric. So it means when you are using a single shock wave, that results in more loss of pressure for the same changes in the flow Mach number. Okay, so one important application of this particular phenomena comes in scramjet engines, where the initial diffuser section of actually a scramjet engine is actually designed in such a way so that multiple reflections of incident and multiple reflections of shock waves takes place. Similarly, if you want to design the diffuser section of a wind tunnel, okay, so in the diffuser section of a high pressure wind tunnel also, we try to design it using the shock reflections, okay, because shock reflections will give us better preservance of the pressure. There will be less pressure drop. Okay, so now with this we will stop, and then we will have further discussion in our next lecture.